All right, here's our second Gauss's law problem. I wrote a checklist on the left. I've already drawn the shape for what we're considering, and I drew it in two ways. I did a side view down here, and I did a perspective view up top. I don't think that the perspective view is very helpful. It's just looking at a sheet of paper at a weird angle. For our purposes, I will focus on the side view option, but I will double back and look at the perspective one as well. Drawing the electric field. The electric field points straight away from the surface. Notice the nice perpendicular nature right there for each and every one of these. I'm looking at how much the electric field is pointing away from the surface. It'll be the same deal up here, but it'll look kind of weird with perspective. I'm only going to draw 9 arrows on each side. And then you can't really see all of them on the other side. All right. That is our electric field pointing out through on both sides of a big flat surface. Drawn the electric field. Next, drawing the Gaussian surface around those charges. Now, side view first. I'm going to draw it like that, which is not very convincing because this looks like a 2D surface. It doesn't look like it's in 3D space. So I'm going to redraw it up top. And here you should be able to see that what I'm drawing is a cube. All right. It's a cube with electric field pointing through this surface and pointing through this surface. It doesn't point through the side surfaces. It does not point through this surface because the electric field is parallel to that surface. It's running along it, not pointing through it. So the Gaussian surface is actually two surfaces. It's this top one, and this bottom one, which I'm going to say the area of the Gaussian surface is equal to 2L squared. All right, done. How much charge is enclosed? Change colors for this. The charge enclosed is going to be this blue rectangle. That is, here's a side view of it down here. Okay. We're dealing with the surface charge density, so that's represented by sigma, is some charge per unit area. And the area that it is covering is only L squared in this case. So therefore, Q enclosed will be equal to lowercase sigma multiplied by L squared. Done. Solve for the electric field. New color. Let's do this in orange. I always like that orange color. Gauss's law first. The electric field, when we have a nice symmetrical situation like this, multiplied by the area of the Gaussian surface that it points through, is equal to the charge enclosed divided by the permittivity. and it's going to be a free space in this situation. The area is 2L squared. It'll be electric field twice L squared is equal to Q enclosed. Q enclosed is the charge density per unit area multiplied by L squared. Don't forget that permittivity. There's an L squared on both sides. And rewrite electric field is equal to the charge density per unit area divided by twice the permittivity of free space. And that is away, which could be up or it could be down, depending on if you're above or below. If you're above, upwards is away, and if you're below, downwards is away. And that is our electric field near a sheet of charge. I'm going to do a follow-up. And for the follow-up, I'm going to consider what's called a parallel plate capacitor. Okay. And I'm going to just do the side view on this new one. In this follow-up, we've got a positive plate here, and we've got a negative plate here. Because of the positive plate, it creates an electric field upwards in this direction, and downwards in this area. And way down here, it also creates downwards electric field, like so. Now I'm drawing all of those arrows as close to the same size as I can freehand because there is no spatial dependence in this equation. So going away, I'm still getting the same effect, as long as it still looks like a large sheet from that perspective. Next, the negatively charged plate. It's negative. So instead of being away, negative will mean inwards. So down here, inwards will be up. Next level up, inwards will be down towards the blue plate. And at the top, inwards will also be down. Let's compare these. These cancel. These cancel. And in the middle, I'm seeing twice the effect at each location. So that the electric field inside what is called a parallel plate capacitor, the electric field inside will be 2 times that, which is sigma over epsilon naught. And the electric field outside is 0. I didn't draw an arrow of directionality. Now that I've done that, I need to say the direction. It's from the positive to the negative side. And outside, there is no direction needed for something that has 0 value, 0 magnitude. Okay? Just to clarify, that's a bunch of results really quick. The red results are for a parallel plate capacitor, which is 2 very large sheets of opposite charges, equal and opposite charges. And in the orange, we've got the electric field is charge density divided by twice the permittivity of free space. away. And that could be upwards or downwards, depending on if you're considering above it or below it. Thank you very much.